Hello and welcome back to Calculus 3, section 11.9 on curvature and normal vectors. So when we have the curve in space, any kind of curve, we said it can represent a path, and we talked about the spring, what was the helix, a slinky, and stuff like that. Right? We want to know the curvature. Now, what is curvature? Curvature is how fast the line turns. What do you mean, how fast? Well, if you take a look here, right, there is some curvature to it because there is somewhere far away a circle that can fill that part with a radius, and that curvature shows there is a curve there, right, the circumference of the circle. Now, it changes at every location, so there should be a circle far away or close by. Now, if it turns a lot, right, the circle is much smaller, the one that fills in for certain. So, for instance, there is less curvature here than less curvature there, more curvature there because it turns faster. So, what is curvature? Curvature is quantification of how much the line turns. And we use two different forms, one to define the concept, and then one to do calculations. When we are talking about the concept, we want to define the concept through the through arc length, because we know how to compute the length of the curve, and each one of those little delta x pieces was giving us the arc length, which we are going to call delta s. So we can parametricize the curve through the arc length, and then the larger the number means that the delta s turns more than in the pieces where it's flat. We should also have the common sense of the concept that when curvature is 0, line is straight, right? And then whatever number we get, right, that is bigger than 0, we are going to have some curvature. So now let's see what the formulas are like, and let's do some calculations with those formulas. So first off, let's define curvature. Again, this is not the way you are going to compute stuff. This is just the definition, and then we will fix that definition so that we can actually use it. So let R describe a smooth parametricized curve Now this goes for R2, R3, R8, whatever. So if S denotes arc length, and vector t hat is the unit vector, right? So that we know it's r prime over the r prime magnitude is the unit tangent vector. We know this one from before. The curvature is given by S is equal to the absolute value, the magnitude of the derivative of the tangent vector in terms of the arc length. I don't know, I would argue it's simple to understand that, because here is your line that is parametricized, line S, and then you have the unit tangent vector t, right? So this is your vector t hat, and now you see that this vector t hat turns, as it goes around this curve S. So how fast it's the first derivative, right? How fast something turns, that would be the first derivative. So we see in this case that we have the definition. Now, we are not going to use this to calculate curvature. We are going to use curvature in terms of t. So what I'm going to do is I'm going to take this unit tangent vector, divide by t, and then ds divide by t as well, right? And when I do that, I get 1 divided by velocity v times dt, like that, right? Which gives us the t prime divided by r prime. So this is actually the proof, the transformation from the arc length into the parametrization by the parameter t. So now we can state that as a theorem, which is technically just a formula that k of t will be calculated as the absolute value of t prime of t, right, the magnitude divided by the magnitude of r prime of t. So this formula doesn't actually defines what we are working with, but it does give us a way to compute it. So to understand the concept, we use the upper definition. To compute things, we use the one on the bottom. So now I want to calculate the curvature of a circle. So find the curvature of the circle. All right, so for that I need r, which is going to be given as a cosine t, a sine t. So we see that I'm working on a general case, like this would be at some problem for the honors option could be this one, where you solve the question for every circle out there. Now the curvature in a circle should be constant everywhere, because the circle is circle has a constant curvature. That should be common sense. So ellipse, which is general circle, right, would have a and b in front of cosine and sine, and that one does not have a steady curvature, because when you draw ellipse, right, it curves more on these ends than on top and the bottom, right? So curvature is bigger on left and right, the way I drew this ellipse, than on top and the bottom. But the circle, right, the curvature should be the same everywhere. So now what I'm talking about is the circle of radius a, and I just want to figure out its curvature. Well, we need to figure out our tangent vector. So for the tangent vector, we need our r prime. So r prime is going to be negative a sine t, a cosine t. So that's our r prime. And then we need also magnitude of r prime, not just for the formula, but also to find the tangent vector. So the tangent, so this is the square root of negative a sine t squared plus a cosine t, everything squared, which just gives us a eventually. So what I have a squared times sine squared t plus cosine squared t, and that's 1. So the magnitude of r is just a. So now to find the unit tangent vector, we take our r prime, which is negative a sine t, a cosine t, and we divide that by r, the magnitude, and what we get is negative sine t cosine t as a vector. There's some lag. So now curvature. Nice. Patience. Yeah, pardon. So the curvature is going to be the derivative of vector t, magnitude, divided by the magnitude of r. All right. Well, let's find t prime first. I'm using the hat because it's a unit vector. When I find its derivative of negative sine t is negative cosine t, and derivative of cosine t is negative sine t. There we go. So now, to find the curvature, I will have to find the magnitude of t prime, which I hope you all see it's 1, right? Negative cosine t squared plus negative sine t squared, and that's 1. So what I have is 1 divided by a. Because we calculated r prime already, magnitude is a. So curvature is 1 over a. For the circle. So if your radius is 10, curvature is 1 over 10. If the radius is a half, curvature is 2, and so on. So the curvature of a circle depends on the radius of the circle, and hopefully you see that the smaller the radius, the bigger the curvature, the bigger the radius, the smaller the curvature, because they're inversely proportional in this case, which makes sense. The smaller circle turns quicker. You see over here, you can fit a circle, right? Well, actually, let's just draw and understand. If I put a small circle here and a large circle here, observe that if you use this to make a road or a pulley or whatever, right? This turns quick, 90 degrees. Over here, it takes time. See, there's a lot of distance over here that you have to cover to make the turn. Over here, it's much shorter. So this one over here turns faster. Smaller radius, let's say radius of, as you can see, half of is going to be 1 divided by a half, which is 2. So curvature is 2 in this case, if radius is 1/2. In this case, if radius is 2, curvature is 1/2. So smaller curvature for the bigger circle because it takes longer to turn, where for the smaller circle, the bigger curvature because it's quicker to turn, and the curvature measures how fast you turn. Here's another example. Prove that k of t equals 0 for a straight line in R3. Go. So you know what the parametric equation for the line is. If you did any quizzes,